Hello, my dear students, and welcome. Today, we're going to tackle a very important topic from organic chemistry, the preparation of diazonium salts. Now, I know the name might sound a little complex, but trust me, by the end of our session, it's going to be crystal clear. So are you all ready? Let's begin.
But before we dive in, let me ask you something. Have you ever looked at your colorful t-shirts, or maybe the ink in your pen, and wondered, how do they get these bright, beautiful colors? Well, the secret, it often lies in a very special chemical reaction that we are going to study today. And believe me, the chemistry behind it is just fantastic. You see, for a long time, chemists were facing a big problem. They had these aromatic compounds which were, well, too stable. They were so content and unreactive, they just wouldn't undergo the reactions that chemists wanted them to. So a clever trick was needed to sort of wake them up and make them useful.
And the solution they came up with was truly brilliant. They figured out a way to take a very stable molecule and, just for a little while, transform it into a super reactive intermediate. This new molecule is so full of energy, it's ready to change into all sorts of other useful things, like the very dyes we were just talking about. The specific problem child here was a group of compounds called aromatic primary amines. A classic example is aniline. You see that amino group, the negative NH2 group? It's bonded very strongly to the aromatic ring. You can't just pluck it off and put something else in its place. This stability was a major roadblock. Chemists needed a way to activate that specific spot. So how did they crack this problem? Well, they developed this process to create that super reactive intermediate. And the name of this process is extremely important for your exams. It's called the diazotization reaction. Let's find out what this word really means.
Okay, for your board exams, this is the definition you need to know. Diazotization is the treatment of aromatic primary amines with nitrous acid in a cold, acidic solution to form thermally unstable diazonium salts. Now, please pay close attention to those words, cold, acidic, and thermally unstable. These are the secrets to making the reaction work.
And this brings us to the reaction conditions. My dear students, these are absolutely non-negotiable. If you change even one, the whole thing will fail. First, you must start with an aromatic primary amine. Second, the reagent has to be nitrous acid. Third, the whole thing has to happen in a strong acid. And finally, and this is the most critical part, the temperature must be kept very cold. We're talking 0 to 5 degrees Celsius. This low temperature is extremely important, and we'll see why in just a moment, so keep that point in your mind.
So what's actually going on inside that cold reaction flask? Before we get into the detailed chemical mechanism, let's try to understand it with a simple analogy. This will really help you to remember the whole idea for a long time. Just think of diazotization as a kind of molecular surgery. Our patient is the stable aromatic amine. The surgeon performing the operation is the nitrous acid. And what's the goal of this surgery? It's not to fix something permanently, no. The goal is just to create a temporary but highly reactive site on the molecule. This mu site, the diazonium group, gets the molecule ready for the next operation, which is making those wonderful colors.
So please understand this crucial point. The diazo group is not our final product. It's just a temporary reactive handle. It's like a special attachment that makes the molecule willing to do new things, reactions that the original stable amine would have simply refused to participate in. It's a fantastic intermediate, isn't it?
Okay, now for the actual chemistry, the step-by-step mechanism. Don't worry, it's quite logical. First, in the strong acid that we're using, our nitrous acid picks up a proton. Simple enough. Second, this protonated acid then loses a water molecule. And what does it form? It forms a very reactive species called the nitrosonium ion, NO+. This is our real surgeon. Third, the lone pair of electrons on the nitrogen of our amine attacks this surgeon, the nitrosonium ion. And finally, after a few quick rearrangements and losing another water molecule, we get our target, the diazonium salt. All right, so we've seen the definition, we've seen the conditions, and we've even looked at the mechanism. Now, let's tie everything together and get back to our very first question about those beautiful colors and dyes. You know, the best way to learn chemistry is to see it in your mind. So to really understand this and remember it for your exam, let's build a clear mental picture. Let's visualize this transformation step by step. So first, just imagine the starting material. We have our stable aromatic ring, and attached to it is that calm, happy amino group, minus NH2. Let's give it a color in our minds. Let's say it's a calm, stable blue color. It's perfectly happy and unreactive just as it is. Now here comes the action. Imagine a wave of yellow nitrous acid, which we just prepared in that cold acidic solution. Imagine it sweeping in. This is our reagent, our surgeon, and it's coming to do its work on that calm blue amino group.
And what happens next is a complete, dramatic change. That calm blue group is gone, and in its place, we now have a vibrant, energetic, unstable red group, the N2+ group. This is our diazonium salt. Using this mental color change from calm blue to energetic red is a great way to remember the transformation from a stable molecule to a highly reactive one. Now here is the most beautiful part of the story. This instability, this energetic red nature, is actually the diazonium salt's greatest strength. Because it's so unstable and it's such a good leaving group, it becomes the perfect starting point for other reactions, especially the reactions that create the intensely colored azo dyes that are used all around us. Now, a question I get from many students is, "Sir, why does this reaction only work for aromatic amines? Why not for aliphatic ones?" It's an excellent question, and the answer is just one word: stabilization. You see, in an aromatic diazonium salt, that big aromatic ring helps to stabilize the N2+ group through resonance. It becomes metastable, meaning it's stable enough for us to handle and use in the next step, but not so stable that it becomes unreactive again. Aliphatic amines, on the other hand, have no stabilizing ring, so their diazonium salts are so incredibly unstable that they decompose almost instantly. They are of no use to us for making dyes.
All right, we have covered quite a bit of ground today, so let's do a quick summary. What are the most crucial points that you absolutely must remember for your examination?
I want you to remember just these 3 things. First, the core idea. We take an aromatic primary amine, we react it with nitrous acid in a cold acidic solution, and we make a diazonium salt. Simple. Second, the mental image. We turn a calm, stable blue amine into an energetic, unstable red intermediate. And third, the main use, this unstable red intermediate is the essential key to making all those colorful azo dyes.
If you can just hold on to these 3 simple points, the core idea, the mental picture, and the real-world application, I promise you, this entire topic of preparing diazonium salts will feel much, much lighter and far easier to master. All the very best.